I'm sure you've heard the news, everything around us is made up of waves. But what does that really mean? Let's break down the science behind energy, frequency, and wavelength. Let's start simple. Imagine you're at the beach, watching waves roll in. The distance between each wave, that's the wavelength. The number of waves that hit the shore every second, that's the frequency. And the bigger the waves, the more energy they have. Now swap ocean waves for something you can't see, like light or sound. Light waves with short wavelengths and high frequency carry more energy. That's why ultraviolet light can give you a sunburn, but red light can't. In sound, higher frequency means a higher pitch. Ever wondered why a whistle sounds different from a drum? It's all about frequency and wavelength. Energy, frequency, and wavelength are like three best friends. In fact, there's even a formula that links them. The higher the frequency, the shorter the wavelength, and the more energy in the wave. That's why X-rays can see through your body. Tons of energy, super short wavelength. Now that we've uncovered the basics of waves, let's see how they shape the world of chemistry. Every chemical reaction, like a glowing firefly or rust forming on metal, starts with atoms and molecules interacting. But what decides how they behave? You guessed it, energy, frequency, and wavelength. Inside every atom, electrons orbit the nucleus at specific energy levels, like rungs on a ladder. Let's dive deeper into X-rays. X-rays are a type of electromagnetic wave with very short wavelengths and high frequencies. Because of their high energy, X-rays can pass through most materials, including soft tissues in the human body, but are absorbed by denser materials like bones or metals. This is why X-rays are used in medical imaging, to create pictures of the inside of our bodies. When X-rays hit a detector after passing through the body, bones appear white because they block more X-rays, while softer tissues appear darker. In chemistry and physics, X-rays can also be used to study the structure of crystals and molecules, revealing the arrangement of atoms in materials through a process called X-ray crystallography. When an atom absorbs just the right amount of energy, often as light with a specific frequency, an electron can jump to a higher level. This is called excitation. When the electron falls back down, it releases energy as light. The color of that light depends on the wavelength, unique for each element. This is where spectroscopy comes in. Scientists shine light on substances and see which wavelengths are absorbed or emitted. Each element leaves a fingerprint, a unique pattern of lines based on its atomic structure and the energy transitions of its electrons. That's how we know what stars are made of, even from millions of light years away. In chemical reactions, the energy carried by waves can break bonds or help form new ones. For example, ultraviolet light can split apart molecules in your skin, leading to a tan or a sunburn. It's all about matching the right energy and frequency to the bonds in those molecules. So the next time you see a rainbow, a neon sign, or even a glow stick, remember, you're witnessing the chemistry of waves at work, shaping the world at the tiniest scales.